Okay, number
Um,
theory office hour.
yeah. So I have a question. This is from homework session 3.5, question 5.
Which section?
3.5,
Okay.
page 114.
Okay, so this is section 3.5, number
5.
5. So we want to find all primes for which -2 is a quadratic residue. So you want to evaluate -2 over p, which is the same as, because -2 is -1 times 2. So this is the same as -1 over p
And 2 over
times
p.
2 over p. Okay?
Yeah. So then we can use the green symbols.
Well, the Legendre symbol tells you whether or not something is a quadratic residue.
Okay.
So -1 over p is 1 if p is congruent to 1 mod 4, and -1 if p is congruent to 3 mod 4, which is the same as saying 1 if p is congruent to 1 or 5 mod 8, and -1 if p is congruent to 3 or 7 mod 8, right? These are the same thing. Okay?
Okay.
And 2 over p is 1 if p is congruent to ±1, that means 1 or 7 mod 8, and -1 if p is congruent to 3 or 5 mod 8. So this -1 over p times 2 over p. So what are the cases? P congruent to 1 mod 8, p congruent to, p is a prime, so it's an odd number. P is congruent to 3 mod 8, p is congruent to 5 mod 8, or p is congruent to 7 mod 8, right? Those are the cases. So if p is 1 mod 8, -1 over p is 1, and 2 over p is 1. This is 1 times 1, or 1. If p is 3 mod 8, this is -1, this is -1, so the product is 1. If p is 5 mod 8, this is 1, this is -1, so you get -1. And if p is 7 mod 8, this is -1, this is +1, this is -1. So these are the cases. So the answer is -p over 2 is 1, if and only if, when you get a 1, when p is congruent to 1 or 3 mod 8. Or sorry, -2 over p. Another way of saying this is -2 is a quadratic residue modulo p, if and only if p is congruent to 1 or 3 mod 8.
Okay. So this is the same way as using quadratic reciprocity.
Sorry?
So so we submit using Lagrange symbol, right? So
Yes.
this is the same way of using like the quadratic reciprocity.
Well, you use quadratic reciprocity when you have p over q, where p and q are both odd primes. So you cannot use quadratic reciprocity here. But we do use always the Legendre symbol.
Oh, because in the homework is asking to use the quadratic reciprocity, but yeah, it's okay.
Oh, yeah. So I guess what I meant was just to use the Legendre symbol. So
Okay, and we can, mhm.
for problem 6, you need to use quadratic reciprocity, and not just the Legendre symbol.
Can we go over number 6?
Yeah, sure. So we want to find all primes for which 3 is a quadratic residue. So we want to evaluate this Legendre symbol. So this divided into 2 cases. So case 1 will be when P is congruent to 1 mod 4. And case 2 will be when P is congruent to 3 mod 4. Okay? So this will be case 1. And if P is congruent to 1 mod 4, then this is just P over 3.
Mhm.
You can flip it. And what do you know about the quadratic residues mod 3? So mod 3, there are only 2 non-zero congruence classes, 1 and 2, and 1's a quadratic residue and 2 is not. So this is equal to 1 if P is congruent to 1 mod 3, and 2 if P is congruent to 2 mod 3. And another way of saying this is that if P is congruent to 1 mod 4 and P is congruent to 1 mod 3, this is 1 if P is congruent to 1 mod 12, because if you're congruent to 1 mod 12, you're 1 mod 4 and 1 mod 3, and it's minus 1 if P is congruent to 5 mod 12. Because if you're 5 mod 12, you're 5 mod 4 or 1 mod 4, and you're also 2 mod 3. So that's in this first case. So, and this is actually, we're using here the Chinese remainder theorem. Because, for example, if P is congruent to 1 mod 4 and 2 mod 3, that's the same as P is congruent to 5 mod 12. And then in case 2, P is 3 mod 4. So 3 over P, so both of these numbers are 3 mod 4. So when you take the reciprocal, you get a minus sign, minus P over 3. So now this is 1 if P is congruent to 2 mod 3. Because if 2 mod 3, this is minus 1 times minus 1. And if P is congruent to 1 mod 3, this is minus 1. So P congruent to 3 mod 4 and 2 mod 3, this is 1. If P is congruent to, what numbers are 3 mod 4 and 2 mod 3? 11. P congruent to 11 mod 12. So 3 mod 4 and 2 mod 3 means 11 mod 12. And 3 mod 4 and 1 mod 3 means P is congruent to 7 mod 12. So if you look at this and you put this all together, 3 is a quadratic residue mod P. This equals 1 if P is congruent to 1 or 11, which is the same as plus or minus 1 mod 12, and it's minus 1 if P is congruent to 5 or 7, which is just plus or minus 5 mod 12. So this is using quadratic reciprocity to determine all primes for which 3 is a quadratic residue.
Good morning, Professor.
Morning.
Can you please solve the question number 4 from the same page, 114 page, question number 4?
Sure.
Thank you.
So section 3.5, number 4, want to prove x squared minus 2 times x squared minus 17 times x squared minus 34 is congruent to 0 mod p, solvable for all p. So if you look at this, you notice if 2 is a quadratic residue mod p, this has a solution. So if 2 over p equals 1, then there exists an x such that x squared is congruent to 2 mod p, right? Right, because this means 2 is a quadratic residue mod p. So there's an x such that x squared is congruent to 2 mod p, or equivalently, x squared minus 2 is congruent to 0 mod p. And let me call, this is just some polynomial. Let me call it f of x. So if x squared minus 2 is 0 mod p, then f of x is congruent to 0 mod p, because when you plug in x over here, you get 0. This is 0. So if 2 is a quadratic residue mod p, then this has a solution. If 17 is a quadratic residue mod p, then there exists an x such that x squared is congruent to 17 mod p. As again, this is just the definition of a quadratic residue. And so x squared minus 17 is congruent to 0 mod p. So if you plug in that x, f of x is congruent to 0 mod p. So if either 2 is a quadratic residue mod p or 17 is a quadratic residue mod p, then this congruence has a solution. So the only other case is when both of these are not quadratic residues. If 2 over p is minus 1 and 17 over p is minus 1, then, and now you observe 34 is 2 times 17. So 34 over p is 2 times 17 over p. These are Legendre symbols. This is 2 over p times 17 over p. These are both minus 1. Minus 1 times minus 1, which is plus 1. So that means that there has to exist an x such that x squared is congruent to 34 mod p, which means x squared minus 34 is congruent to 0 mod p. And this is a factor of this polynomial. So f of x is congruent to 0 mod p. So we've exhausted all the cases. If 2 is a quadratic residue, this has a solution. If 17 is a quadratic residue, this has a solution. If neither of these is a quadratic residue, then 34 is a quadratic residue using the multiplicativity of the Legendre symbol. So this has a solution, and so f of x has a solution. And that's the end of the proof.
Thank you.
Professor,
Yeah,
for the review, in proof number 2, you don't have to solve, I just have a question. So I have to prove like 2 is not a primitive rule of modulo 31. So if it's enough, if I show that the order of 2 is now p minus 1, like trying the divisor of 30.
I'm sorry. Which proof on the review sheet?
Number 2.
Prove that 2 is not a primitive root modulo 31. Well, I guess you could just use the theorem about 2, computing the Legendre symbol for 2. Otherwise, you would have to use something like, well, yeah, I mean, so proof number 2. 2 over 31 is congruent to what? Minus 1 to the, no, I don't want to use that. I guess just, so 31 is congruent to what? Is congruent to 1. Sorry, it's congruent to minus 1 mod 8. Oh, I'm sorry. I was thinking, that's completely wrong. I was thinking of quadratic residues. So proof number 2. So the order of 2 modulo 31 is always a divisor of 31 minus 1, or 30. So must show the order of 2 is exactly 30, not just a divisor of 30.
Yes, that's
I
what I want
guess
to say.
you just have to take powers of 2. So 2 to the first is congruent to 2 mod 31. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. 2 to the fifth is 32. But 32 is 1 mod 31. Oh, sorry. Must
What
show
about
that
if I try the
this is not-
divisors of 30?
So this says that
Oh,
2 has order 5, not 30.
yeah.
So 2 is not a primitive root.
Okay. So what I was saying, for example, if the prime number was bigger than 31, right? So can I just try like the divisors of p minus 1? So for
Yes,
example, here 30 is 5, 6, 10, 3.
exactly. Yes. You would just
Okay.
have to try 1, 2, 5, 6,
3, 10,
10.
and 30.
Yeah, 1, 2, 3,
Mhm.
5, 6, 10, 15. Yeah. If none of those work, then the answer has to be 30.
Okay, and we can do the same thing for problem number 2, right? So in case the number is big, like we can do the same method, and if the order is p minus 1, so then it will be a primitive fruit.
Exactly. That's exactly correct.
Okay. I don't know if Norma or Miguel have any question.
Excuse me?
I don't know if the other ones have any question for you.
Okay, I don't know.
I don't. I'm just here to watch.
Sure.
Oh, Professor, are you recording this? You are.
Yes.
Will you be posting this?
Yeah, well, no point to record it if I don't post it. Yeah, someone asked me to post it, so I will.
Roger that. Makes it.
Okay, Professor, that's it for me. Like, if I have any other question, then I will join the night.
Yeah, I'll be
Maybe.
back at 7 o'clock.
Okay, thank you, Professor.
Okay.
Bye.
Any
Thank you,
other
Professor.
questions?
Enjoy the rest of your day.
Any other questions?
Thank you, Professor.
Okay, so I'm going to have another
Okay.
hour at
Enjoy the
7.
rest of your day.
Okay. All right. Bye-bye.
Roger that. Thank you.